Welcome back for this video on what is probably the last, what I would call big rule in differentiation, which is known as the chain rule. And for the chain rule, it states that given a function in the form f of g of x, so your composite functions. And how we state that is f of g of x. And that of becomes a very important word to look for when thinking about this new chain rule idea. What the chain rule says is that the derivative with respect to x of a function in this form, f of g of x, will equal f prime of g of x times g prime of x. And so when looking at this rule, notice you are differentiating both functions in the problem, both the outer function of the composite and also the inner function of the composite. And essentially all you're doing is just taking the derivative of the outside times the derivative of the inside. And the idea behind the chain rule is that when given a composite function, I make one function an input on another. We differentiate one layer of this setup, or one function, at a time, and then you chain them all together using multiplication. So let's take our first look at an example of putting this into practice. An example we'll use is the derivative with respect to x of sine of 3x. And recall, one of the basic rules you would have started with is the derivative with respect to x of sine of x is just cosine of x. But that has to kind of tell you that when I'm looking at the derivative of sine of 3x and sine of x are not the same function, not the same graph, so their derivatives, the function that's going to decide the slope of that original function, they can't be exactly the same. X versus 3x is a big difference. So what we're going to do is we're going to define this function based on this outside-inside idea. And think of again how we read this function, sine of 3x. The sine function will be our outside, and the 3x will be the inside function. The inside is always in order of operations what would get done first, outside's what would get done last. And for a little organization, we'll make a note that the outside function, sine of 3x, inside function, 3x, and then we're going to differentiate those one at a time and chain them together. So we'll start, for the outside, recall that derivative of sine is just cosine. So derivative of that outside function will be cosine of 3x times the derivative of the inside function, and the derivative of 3x is just 3. And there's our final result based on the chain rule. Our derivative is 3 times the cosine of 3x. So this rule can get tricky if you're not used to dealing with a lot of composite functions, not as confident on how to read them, and just based on the number of ways it's going to show up, which I'll show through the next few examples. So our first example to follow that up, let's look at the derivative with respect to x of cosine of x squared. A situation where our outside function here, much like with the starting example we had, is the trig function, cosine of x squared. And the inside function, the input to that, is x squared itself. So we differentiate one at a time. Derivative of the outside, cosine, becomes negative sine of x squared times the derivative of the inside function. X squared becomes 2x, and we chain them together with multiplication. And our final result, our derivative, is negative 2x times the sine of x squared. Now I mentioned earlier that there are a lot of ways the chain rule can show up. So let's look at a different way in example 2. And for this one, we'll look at the derivative with respect to x of the function e to the 5x to the 4th power. So you kind of got a power inside of a power. Now the outside function here is e to that power, e to the 5x to the 4th, with the inside function being 5x to the fourth. This exponential form is special. When I say e to the 5x to the fourth power, that phrase in the middle, to the, is working the same way the word of did when dealing with our trig functions. And we'll see one more example after this, where something to the power of something else is just as important for identifying chain rule as the word of is. And so for this one, derivative of the outside, remembering our rules, the derivative for the exponential function base e does not change, so the derivative of the outside is e to the 5x to the fourth, times the derivative of the inside, and that 5x to the fourth becomes 20x cubed. And our final result is 20x cubed times e to the 5x to the fourth power. And so like I said back at the start of that example, let's look at one that's kind of like that. Our third example, let's look at the derivative with respect to x of the quantity x squared minus x to the fifth power. Again, that phrase to the power, x squared minus x to the fifth power, is working a lot like of. So power functions and exponential functions can still require chain rule. And for this problem, the thing happening on the outside is that fifth power. That's the thing I would do last in order of operations. And what's inside that fifth power is this x squared minus x. So derivative of the outside using power rule will be 5 times that x squared minus x raised to the fourth power times the derivative of the inside, and the derivative of x squared minus x is 2x minus 1, and make smart use of grouping to show that we're multiplying by that entire derivative function. And that's it. We're not going to worry about expanding anything, distributing anything. This final expression is our final answer for the derivative. So let's finish up with one last big problem to kind of show you how far we can stretch the chain rule. Now let's look at this function. F of x equals natural log of sine of 5x. And one more time, I'm going to write out how I read that. Again, it's natural log of sine of that final function, 5x. And notice in reading that, I said the word of twice, which tells me I've gone through an extra layer, and I'm actually going to have to use chain rule twice, because I really have two functions that have ended up inside in a particular order. So this one, let's get ourselves organized then. The outermost thing happening here, the last thing in order of operations, would be the natural log. So our outside, natural log of sine of 5x. The next function inside from that, the next layer, is sine. So our next inside function is sine of 5x. But we have something all the way inside of this composite function, kind of the first thing you would hit in order of operations. And so the most inside function is 5x. Three distinct functions, which means we have to chain together three distinct derivatives. Derivative of the first function, derivative of natural log, our rule states, is 1 over the inside of that function. So derivative of natural log of sine of 5x, 1 over sine of 5x. Times the derivative of our sine function, derivative of sine of 5x will be cosine of 5x. And finally, times the derivative of 5x, which is just 5. And then we can start playing around with simplifying this. We can combine the cosine of 5x and sine of 5x into the same fraction. So we get 5 times cosine 5x over sine of 5x. And that is a known trig identity. Cosine over sine of the same input can become cotangent. So our final result, f prime of x, equals 5 times cotangent of 5x. And so as you look through all the examples that were done, what I want to leave you with is when you need to consider the chain rule. And we need to consider chain rule for power functions. We saw that back in example 3. exponential functions. That was back up in example 2. Other situations, we just saw in this big problem, logarithms. Those have inside functions. And also, which we've seen a couple times, trig functions. And if that sounds like every basic derivative rule you've used to this point, that's because it is. The only crossover that chain rule doesn't have is with the product and quotient rule, because products and quotients are other ways that we arrange functions, multiplying or dividing them. Chain rule applies to every composite function that you could possibly write. And every function family you ever learned can be written as a composite function. So that's it on the chain rule. And it's a big rule that takes a while to recognize, but the only way you're going to get to that point is by starting to practice. Thank you for watching.